Hello and welcome back to another LeetCode problem for interview practice. Today we're going to look at LeetCode problem 297 to serialize and deserialize a binary tree. This is a hard problem, and as usual we're going to do our little interview procedure where we first read the problem to understand it. Then we ask for clarifying questions and constraints. Of course on LeetCode we can't ask anybody, so we're going to look at the constraints. Then we will go through the examples. In an actual interview, we might have to construct our own examples. And we'll try to solve basically the problem on paper with those examples to understand how we could approach this problem algorithmically. Then, when we have an idea of how we could implement it, and ideally multiple ideas, we're going to give a runtime and space analysis before we write our first line of code. And then we would ask typically the interviewer for buy-in, which version should we implement, or we make a suggestion which one to implement. And then we proceed with the implementation. We will walk through the details of the implementation, explaining it while we write it, and then step with a mental debugger through our code to try to find any errors and run our example cases through the code without executing the code. And then when we're sure that everything's all right, we will actually submit the code to see if it passes the tests, and then finally all the test cases. So let's get into this. Serialize and deserialize a binary tree. Serialization is the process of converting a data structure or object into a sequence of bits so that it can be restored in a file or memory buffer, or transmitted across the network connection link, to be reconstructed later in the same or another computer environment. Interesting. So design an algorithm to serialize and deserialize a binary tree. There is no restriction on how your serialization or deserialization, can speak today, algorithm should work. You just need to ensure that a binary tree can be serialized to a string, and the string can be deserialized into the original tree structure. Clarification: the input-output format is the same as how LeetCode serialize a binary tree. You do not necessarily need to follow this format, so please be creative and come up with different approaches yourself. All right, so the first thing I want to know is, how are we given the tree? Is it like, are we given the root node? Can the root node be null or none? Are we maybe giving the tree in another form? We could be given the tree in the form of a heap, in an array, for example. Does the tree have any special properties that we can exploit? What are the values of the tree? Is it a doubly linked tree or just a singly linked, where a node only has pointers to its children? Then also, how many children can a tree have? And well, I guess the answer is here, only 2. And so I would clarify those questions, and then we get the answer. We might have 0 or more nodes in the tree, and where the nodes have integer values between -1,000 and +1,000. I assume integer. And each node has a left and a right child. So those are the constraints. So we need to be able to serialize and deserialize a tree. And when we serialize it, we take in a root node, and when we deserialize, we get in a string of data, and we should return a tree node object. Yeah, cool. So let's look through an example tree here. So this tree is not a binary search tree, but it's a binary tree. And so this is given, and kind of this format, I like this format already. I think we might be using this for our serialization. So we have the root node in 1, then immediately followed by its 2 children, 2 and 3. Then come the children of the left child of the root node, and then come the 2 children of the node 3. And each of them also have no children, right? 4 has 0 children and 5 has 0 children. And the output should be the same as the input, because we call serialize and then deserialize on that tree. Okay, cool. So, and in case of the root node, we just have an empty array passed to our test case, I suppose. Okay. Yeah. Cool. So yeah, what I would suggest is we use this array type structure where we actually put in a node and then immediately its two children follow. And if the node 2 has children, okay, let me start over with that. So I think we can solve this in linear time and linear space. And we could do this recursively, where we create a data structure, and I'm just taking some notes here, where we have a data structure that works as follows. That is slightly maybe different from here. Because we know we have a root node. So let's take the example here on the left. We have the node 1. And we know that this node has two children. So in this case, it's the child 2 and the child 3. But we also know that 2 has children. And in this case, they're none and none. But if we nest those children here recursively inside, we could descend in any subtree of the main tree and generate this data structure automatically. So the node 3 will have the children 4 and 5, and the children of 4 are none and none, as are the children of 5, none and none, right? So this would be a serialization of this particular tree. So what we need to do now is we need to come up with, the delimiters that we can use in our tree. Luckily, we know that our tree contains number values. So that means we can use anything that we want. We could just put in the number value here. And for the delimiters, we could just use the square brackets and the comma, for example. A square bracket means after a node means that these are now the children of that node. And a comma just separates two children, right? So let's see. Yes, so here the children of 3 are 4 and 5, and they are separated by a single comma within those square brackets. The square brackets denoting the children of 3. So what we can do is we can just, we find the next opening bracket, opening bracket, and then what we need to do is, need to match that with this bracket here at the end. But actually, we don't even need to do the matching, because we know that if we just follow these nodes, 1, 2, none, we know this is left child, so we create them. And it actually becomes quite easy to do recursively. So I'm just going to have a little helper here for the serialization at first. Node, and we're going to build a result. So we're basically creating the heap, kind of a heap structure now where, well, I keep saying heap because the child of a node is the children of a node are followed by its parents. Kind of, I don't know if that makes sense to you, but that's how I picture it in my head, even if it's not exactly a heap, because we don't have a, well, the indexing is similar as in a heap, the indexing of the children. So what we will do is we will, we'll check if not a node, we are going to append none. Well, actually, we're not going to append anything. We just put the empty string. If we have none, we just put the empty string. Why would we want to parse the word none? We don't have to. Right, the fact there's nothing between a bracket and a comma means there's nothing. So we append 1 and we're done. Otherwise, what we're going to do, we're going to append basically the node value, right? And we need to convert it into a string value, into a string. But we also need to append. What do we need to append? Well, our opening and closing brackets. So we will append this and that. To append the opening one. And then what we do is Well, we need to make our recursive call, right? So we'll call helper on node.left. We need to insert a comma, and we need to call it on node.right. Right. Now I'm thinking, append that. Well, we actually just have to call helper left, helper right. Because when we call the helper function, it will do its own appending of its own values, right? So if node.left is none in the recursive call, we will append an empty string. We're done, and return result. And then finally, we have to put that into a string format. So how can we do that now? Well, we can do that with, let me see. Well, we don't actually have to do anything. We can just return this. Return join helper root. That's what we need to do. Yes. So this will give us something in that format. So how do we reverse that process? I'm going to delete those code comments here. So how can we actually do that? Well, we're getting a string. So what should we do? Well, one thing that we can see is that before every node, we either have an opening bracket or a comma before the node values, right? I see. Well, I think we can make it even simpler for us, because we know that every node is followed directly by its two children. We can actually use a single separator to do that. So we could, if we wanted to, just use a dash, for example. So this is an improvement now, or simplification. So if we have a node with a dash, we know that the next node is its child. Then we know that its next node is the child of 2. So in this case, we have no children. So if we put empty strings, it's just going to be dash dash. Now comes the next child of 1, which is 3. It has a child 4. 4 has no children. So this and this empty space means no children for 4. Then we run into the node 5, and its two children, first child and second child. So does that make sense? 2 has 2, none, and here as well. Yes, and we can delete the last one. So if we do that, then all we need to do is we need to split our string by the dash. That's all we need to do. And we just build a stack out of it. So we say stack equals data.split. And we need to reverse it so that we can consume the stack from the beginning of the string. So what we do now, we have another helper. And all we do is we return helper, and we call it with a stack. So we pop an element or from the stack or value is stack dot pop, right? And now I'm thinking again. And if the value is an empty string, we know this is none, so we return none. Otherwise, we know that we actually have a value, and it's going to be one of those values that were in the original tree. We say value equals int value. So now I'm assuming that we're dealing with int numbers here. It wasn't stated explicitly, but I think we can assume that. And that means we need to actually return a new node, right? Node equals, what was it? A tree node. Node equals tree node. And node.val equals value. I don't see a constructor here. Oh, there's a constructor. Node value. And well, we still need to process. Well, we need to return the node in the end, right? Return node. But we also need to populate this left and right child. And what do we know about it? Well, if we go into the helper method, the first thing that will be returned is the left child, right? So what we'll do is we say node.left equals helper stack. And then after that is done processing, what we will do is we will set the right node, right equals node.stack. And the case where we terminate the recursive call is when you run into basically one of these empty ones. So in our example, what will happen is we will, if we deserialize this string, we split it, and on the stack we will have well, I'm wondering if we do a split on dash, does it? Well, it means it removes all the dashes and gives me the substrings back. So actually, we would have to put a special value in for null. And the way we can do that is by just saying, maybe we mark this as an underscore, right? So an underscore is a none or a null value, something like this. Now, if we split the string by the dash, we get all of the number values, including the underscores. So we'll check if value equals underscore, we return none. Otherwise, the value is an int number, right? Yes, I think, yeah. I think that makes more sense. And yes, so I wanted to go through the example. So we're starting to consume the stack, right? So first we pop out 1. 1 is not an underscore. So we create a new node with the int value of 1. Now we need to assign its left value. And that means we call helper recursively again. Now helper pops 2 from the stack. And since that is the value, again, it creates a new node. And it does another recursive call. And the next value pops from the stack is the underscore. So that means it's none. So we return none. We are now back at assigning the left child for the node with the value 2, which is what we do here. Now we call the stack again to set the right child of the node with the value 2. And we pop the next underscore of the stack and return none. So that means the node 2 has now no left and no right child. And since we're now done, we will actually return this node. And remember, we were processing the left child of the root node 1. And that node has now been created, which is 2. Right? So we just created the node 2 and assigned it as the left child of the node 1. And we have processed the entire string up until here so far. So now what happens is we start processing the right child of the root node with the rest. And as you can see, we create a node with the value 3. It gets the left child 4. Left child 4 has no further children. Then we process the right child of the node 3, and it also has no children. So I think that concludes everything. I'm just going to make sure that there are no typos. So let me just go through this one more time. So serialization. If we don't have a node, right? Or if node is none. Same thing. We append the underscore. That's our marker for no node. Otherwise, we are appending our node value, followed by a separator, followed by the serialization of the left subtree, followed by a separator, followed by the serialization of the right subtree, followed by a final separator in the end. Yes, so I had this example earlier. So there's a final separator at the end, but I don't think that matters. When we do the split, I think it gets removed, so we don't have to process it. So the deserialization, well, we need to basically we need to split the string and then invert the order of the nodes. so that we can pop them from the end. Otherwise, if you pop something from the beginning of the linked list, it's going to be of an array. Then it's going to be an O(n) operation, but we don't want that. So that we just reverse that and then start popping from it. I think that's everything. I don't think we need anything else. In terms of runtime, obviously, every node gets visited once, so it's definitely at least O(n). In terms of space, well, we're constructing either a string, that depends on how many nodes we have, or we're constructing a tree. And in each case, the size depends on the length of the input, which is the number of nodes in the tree. Yeah. Also, the node values are bounded, so they cannot make this explode. But anyways, yeah, so it's O(n) time, O(n) space at least. What is notable is that we not only have auxiliary space that we're using, but we're also using stack space, right? Every time you call a recursive function, that costs some space on the stack. Now, the space needed to serialize or deserialize depends on the height of the tree. So it's technically O of h, but again, h is always smaller or equal to n, so it remains the same. We still have O(n) time and O(n) space, and I think I'm now brave enough to run this code. Hopefully there are no typos, but there are some. Okay. Join helper on root. Let me see. Missing required argument result. All right, so that's something we missed. So we have to give it an empty array to start building up the result, and then we just well, we return the result as well. That's why we can then call join on that. So let's do that. There we go. Okay, let's give it another try. Node is not defined. Do you mean node? Well, yeah. Node. Another typo. I get so impatient that when I'm not in an actual interview, I don't really check the syntax. Yeah. Node.left exists, but argument result. Okay. Fair enough. By the way, another way would be to define the result here, right? And make it accessible inside the helper and then remove it from here. That would also be possible, but then it's not as well, yeah. Maybe we should actually do that. Why not? Let's make this change. So we don't have to pass it in here. Root. And you know, we could just call helper root like so. Could even remove it from the return result. Don't need that. And then we just join the result. We could also do that. I guess it's a matter of coding style, what you prefer. So this is now a method with side effects, because it affects variables that are outside of its scope. Okay, let's run this. Helper right.left, that doesn't make any sense. It needs to node.left. I apologize for all these small errors. And int value. Invalid literal for int with base 10, and it's empty. It doesn't have a value. So maybe that does mean that the last element, because we're adding the result.pop, that means we would remove the last dash, right, that we have, because we're always doing the dash here. Or what we could do instead is we could move that one here. But I think we should, let's just remove it here. Otherwise we would have to remove it here. Which maybe is the better idea. But it's definitely an off by one error because of the splitting. Or maybe not. So, okay, so I don't know exactly what it is. I just took a guess and I don't really know. So, yeah, let's go into the uncomfortable part where we have to start debugging. So, let's see. Let's demonstrate some good debugging skills. So my impatience is clearly being punished here. I'm not able to just rush through and hope that everything works out. Okay, we're getting invalid literal for int with base 10, and it's because we're getting empty string when we do that. Well, when we do that. So we were splitting on the dash. So that means the only thing that can happen, well, I wonder why, how on earth can we run into the problem of an empty string? How do we get an empty string by doing the splitting, right? So let's see. If the node is none, we apply an underscore. If the node is not none, we first put in the value of that node, and it's guaranteed to be a number. Then we append a dash. Then we append maybe an underscore, or maybe another number, etc. So here, but when we added the left subtree, we add another dash. I'm thinking at the end. And maybe if then we come back from a helper method, we then add another dash. So we added a dash too many. Can you believe that? So we added a dash too many. What if we remove this adding of this dash? What will happen then? Well, for good debugging, you need to run through some examples. So what we will get is, we will have node 1 dash 2 dash underscore dash underscore. Right, so this is node 2, and then the left child and the right child. So we are now here. Then we return from the recursive call to the left one. Then we're adding the next dash, and now we start adding the right subtree. So it looks like we added one dash too many. But to be completely honest, I'm not 100% sure. I probably need to run through the complete example, but I'm not doing it now. So let's see. Wrong answer. What did we get? We expected null and null. And we got the wrong. Node.left, node.right. So that was another mistake. Okay, now we got it, finally. All right, yes. So what is the moral of the story? Well, you actually need to run through your examples, even if you think you're smart enough to know that this should work. Chances are you run into issues. And when you do, well, the interviewer is going to note that. And it'll be, oh no, we're doing it again. So we have another error. Okay, this is very horrible. Yeah, I want to kind of see what happens here. So what we'll do is we'll just print the data. And then we're going to print the stack. Let's see what happens here. And submit. The data and the stack. So here we have two dashes. So why could that be? After adding the value. Yeah, that is clearly the mistake here. We shouldn't have two dashes follow each other. So we do this, and then we do call the left one. How could that even happen? How could that even happen? If we get, oh, it's a minus sign. Okay. Oh, the minus sign is screwing us over. Oh, God. Jesus Christ. So we can't use that, right? So, well, what are we going to use? Well, we're going to use the pound sign. How about that? Okay, so, well, turns out you actually need to pay attention when you solve these problems. And I should submit it without the print statements. That was just for debugging, so that's accepted. Let's try it again. All right, well, I shall title this video accordingly. Note to self, don't rush through it. think through it. That is the moral of the story. But yeah, otherwise the implementation is really going to be super easy. So just to recap, you really need to analyze in this problem, you know, which character can you use as separator and which ones are already part of the data that you're storing. And the other one is that if you have some recursive data structure, there's almost always, well, I think there's always a way how you can serialize it, right? Even if this was an n-ary tree where you had an arbitrary number of child nodes, for example, let's say, yeah, actually, let's think about it. So if you have, if you have a tree like this, self.children is, that's a follow-up question maybe. How would you handle the case when you have a tree that can have an arbitrary number of children? Like so. Well, in that case, our left and right doesn't really work anymore, does it? So what we have to do now is we will have to process all of the children, right? For child in range for all children in we basically need to make this more general. For all children in node.children, for each child in children, we have to append this, and then we have to append that on the child of the node, and we have to add that. So that's what we have to do. But because we don't know how many children there are, we need to also encode, maybe use a pipe symbol for that, how many children there are following that. So we will have length children, node.children, right? And so during the parsing, we actually have to check, okay, does our next element on stack have a pipe symbol? That tells us how many children we need to process next. So helper child, yeah, that works out. I think that's correct. So if we go here now, we still split on our splitting string, but when we pop a value out, what we'll do if the pipe symbol is in value, in that case, we have to basically get the value, and the count is a value dot split by the pipe symbol. Pipe symbol. And now what we do is we say count equal, well, we have to convert it to int, right? Count equals int count. And now what we do is here we basically have to iterate as well. So for in range count, and we're going to have to say node.children append, and then we just call helper on the stack, and everything else remains the same, because we know that the recursive reconstruction of a subtree terminates when we when we reach the leaves. So if let's write our tree as in this new format. So we would have one pipe. How many children does one have? 2. Then we're adding the pound sign as a separator. Now comes the first child, which is 2. And it has 2 children, none and none. Right? Now we're processing the right subtree of root. So and that's a child. So we append pound 3 pipe 2 children. It has 2 children. Then we continue adding the 2 children. So it's 4, and 4 has 0 children. Oh yeah, we actually have to do it like this. I have to, let me think about this. 0 children means 0. So We actually never run into a node that is none, right? Because they're all enumerated in the array. So either it's in there or it's not in there. I'm thinking. Yeah, it's, well, yes. So on every node, we actually have the count of how many children it has. Okay, so let's start over. So if the root node 1 has 2 children, the first child is 2, it has 0 children. Now we're processing the right child of root, it's 3. 3 has 2 children. The first child is 4. 4 has 0 children. The right child is 5. We have to add this. Where's my pound sign going? 5. It has 0 children as well. So that's how that would look serialized or deserialized. Serialized. And we still split on basically on the pound sign. And we know that every time we split, this is a node and it tells us how many children it has. So it's a node with 2 children. This is the first child. It has 0 children. So in our recursive call, we pop back. Then we process the second child. It has 2 children, etc., etc. So it processes that. So we actually have to split this every time. So we'll have value and count. And yeah. Can you tell that I'm not in focus mode right now? And yeah, that's pretty much it. So that's how that works. And I think it would work, to be honest. Well, we can actually run the test case, can't we? So we could say print data, and then we run the test case. Let's see what happens. At least we can check the closing parentheses not matched. Okay, there you go. At least we can check if the serialization works correctly. Doesn't have an attribute. Okay, we can't even check that. Node.children equals node, well, it's like this. If node.left, then node.children and node left. So I'm just adding now for a little hack, just adding the children in here. And the other one is the right one, right? Okay. Node.children, node.val plus, oh, this must be a string. The object has no attribute children. Why can't I just write that in the tree? Why not? Oh, sorry, that's down here. So here, yeah, so now we see what to get. So we had node 1 has 2 children, now the first child, and the first child has 0 children, so now follows the right child of the root node. It has 2 children, which are the 4 and the 5, and each one have 0 children. Right, so yeah, maybe you want to implement a test to test this yourself. We could do it like this. Like this. I think that should now run without errors. I'm just adding the children array to the node object. And node the children. Well, now it's complaining there again. Anyway, it doesn't really matter, but you get the idea. If node, or if not node, return, we return nothing. Well, return nothing, the empty string. And then in that case, if not data, return none. That was just the other test case. So yeah, so that's an edge case to consider as well, because this will return nothing, the serialization of that. Anyway, so cool. That's it. Rather long-winded. You've seen lots of errors again. I hope you don't make them. But I also hope that you try to implement this, including the follow-up question. Enjoy.